Hey, what's up, guys? So, welcome to my YouTube channel. So in this video that I'm going to just doing this derivation that how Newton showed the orbit is ellipse. And basically this kind of proof basically is two directions. So this is due to Newton from maybe 400 years ago. So the idea is that if you believe, let's say you believe the force between the two particles or the sun and the earth is some minus k to the r to the n, they say n greater or equal to 1. And you can so this is your assumption. And the second assumption is that they say you have some orbit, right? So you have some orbit where the energy is less than 0. Basically, this means that they say this is Earth, this is Sun, and suppose the Earth is bounded by Sun, and the energy is less than 0. That what Newton can prove is the following: is that if let's say if n is 2, so it's a standard 1 over r squared, then this will imply that the orbit is ellipse. So this proof is very non-trivial. Okay, so we'll go through this. But conversely, I guess that conversely one can show that if the orbit is ellipse, then you can show that n is 2. Okay, so basically this is what make the Newton to be the giant of the science. And the proof is quite cumbersome. It's not easy to prove. Okay, so in this video that I'm gonna go through this proof, and yeah, hope you guys subscribe to my channel. Okay, so the quick derivation is start from the energy conservation. Right. So first we know that the kinetic energy, for let's say we fix some to be on the 0, 0. Let's consider a plane, and then let's say this is Earth, and this is x and y. And then we want to change it to, let's say, r and phi. So these are polar coordinates. Okay, so your kinetic energy is this. So let's say we take mass to be 1. Okay, so the Earth to be mass to be 1 just for convenience. Okay, and so first, the first thing what you need to do is change the polar coordinates of energy to Cartesian form to polar coordinate. Okay, so this is the results. Okay, so I'm not gonna derive this, but this is a very simple calculus. You just write down x equals to r cosine phi, and y equals to r sine phi, and you're doing the x dot, so it will be r dot cosine phi minus r dot sine phi dot. Sorry, it's r. Okay, and the y dot is basically r dot sine phi minus r cosine phi dot, and you just sum over squared. Okay, and you will plus, and you will see the cross term canceled, and you can prove this. Okay, and so the energy conservation will give you the following equation: plus V equals to E. Right, so it's total energy and your potential. Okay, so you start from this. Right, but the problem is that this is only one equation. So you need to prove if you want to prove the orbit is ellipse, what you need to prove is you need to write r as a function of phi. Okay, right? But this derivative comes from the time, right? So you need another equation to connect r and phi. Okay, which is like the Kepler area law. Okay, because we know that this force is concentric. Okay, so which means that r squared phi dot is constant. Okay, let's call this constant h. Okay, so this is the area law. Basically, this area law says it's r, right? It's phi, and then so the small area that generated by given time is this small infinitesimal, which is constant. Okay, so you have these two equations, right? So you can replace this phi dot to be with h divided by r squared. Okay, so let's quickly do a derivation. So let's see. So you have this, plus v equals to e. Right, so now you have phi dot equals to h divided by r squared. Okay, so you just replace. So what you can get is half of r dot squared plus r squared, h squared r to the fourth plus v equals to e. So get the half of r dot squared plus h squared divided by r squared plus v equals to e. Okay, so the next thing what we need to do is we need to replace this r dot to be r to write a function of r and phi. Okay, so r dot is dr dt, right? We need to write dr d phi dt. And we want to have this, right? So this is dr d phi dot. Phi dot is h divided by r squared. So it's dr divided by d phi, h divided by r squared. And then we can plug in. Okay, so get half of dr divided by d phi square h square r to the fourth plus h square r square plus v equals to e. Okay, so from here that we not yet finished, but we are very close to some differential equation of this, right? Okay. Now we can replace this v to be the vector potential, right? Sorry, not vector potential, the gravitational potential. So let's write v to be minus gn divided by r. Okay. So what we can get is the following: dr d phi square, right, plus right, you can see if you can see this, if I times this h squared cancel, then I get r squared plus 2v by r squared divided by h squared equals to 2e r to the fourth divided by h squared. So this is r to the fourth, right? Because I times r to the fourth to cancel this. Okay, so now I can replace this. Okay, so from here, what I can get is the following. We get dr d phi squared plus r squared minus 2gm r cubed divided by h squared equals to 2e r to the fourth h squared. Okay, so now the rest hopefully is non-trivial, right? Because you need to solve this equation. And then it's not easy to solve, right? Because this is square, so it's non-linear term. Okay, so the very weird thing to solve is you make some weird substitution. Okay, so the step is very interesting, just that u equals to 1 over r. Okay, so this is somehow like standard way that someone come up with to solve this kind of equation. Okay, so let's see. Let me just copy this equation here. H squared 2er to the fourth h squared. So let's say r is u is 1 over r, right? So dr d phi will be just dr du d phi, right? So this is minus u to the negative 2 du d phi. Okay, so we can plug it. Okay, so what we can get is u to the negative 4 du d phi squared plus u negative 2, right, minus 2gm u negative 3 h squared 2e u negative 4 h squared. Okay, so what you can get is du d phi squared plus u squared plus 2gm h squared u plus 2e h squared. Okay, so let's write it as du d phi squared equals to negative u squared minus 2gm h squared u minus 2e divided by h squared. So this is some quadratic function in u. Okay, so start from here, that the rest is just like the magic. Okay, the magic happened. So now we need to solve this. Okay, so now we differentiate both sides by d phi. Okay, so okay, so what we can get is 2 du d phi d squared du squared d phi squared equals to negative 2u to gm h squared du d phi. Okay, so now we can cancel this du d phi. And delete this 2. Okay, so what we can get is this equation. Du squared d phi squared plus u equals to negative gn divided by h squared. Okay, and this is simple to solve, right? Because this is just a second differential equation, but comes with just constant term. Okay, so let's quickly solve it. So okay, h squared, right? So you can just rewrite as this, right? U plus gm divided by h squared d phi squared plus u plus gm divided by h squared. Right, so that means these guys is the second differentiation equation, right? So u plus gn divided by h squared must be combination of cosine and sine. Okay, so this answer must be, let's say, some constant times cosine phi minus phi 0. Okay, so if you write u to be 1 over r, then you derive 1 over r equals to some constant cosine phi minus phi 0 minus another constant. So it's 1 over r. So it's 1 over r equals to cosine phi plus something. Okay, and this guy is ellipse. Okay, so basically this is just the why this guy is ellipse. This is the proof. Okay. Oh, okay. I think I forget. I missed one term here. So this should plus. Okay. Sorry, it should plus minus plus. So this is plus, right? So it's yeah. So when it's plus, then it's ellipse. Okay, so 1 over r will be just gn divided by a squared, and you can 1 plus e. So this is, I think it's the c over a in that ellipse. Okay, so it's cosine phi minus phi 0. So this is ellipse. Okay. And but from here that you need to go back and show that the energy is negative. Okay. So in order to do this, you need to do some extra work. Just to show that this is really ellipse when energy is less than 0. Basically the energy is less than 0 will force this equation has 2 real roots. Okay, so this is the important thing you need to show. And basically, let's see. So if you plug this equation back, let's say this equation back, you plug this equation, go back to, let's say, this equation. Okay. Then what you can find is the following. You can find that e squared is 1 plus 2e h squared divided by g squared m squared. Okay, which equal to 0, 0. And right. Okay. Yeah, and let's say you can also solve this equation. Okay. So this is the reason is why the 1 over r squared term will give you ellipse. And I mean, but let's say conversely, right? Conversely, if you solve here, so if you directly go back to, let's say, here, if you directly go back to here and just do what we have done, then you can show that if you plug your answer to be 1 over r equals to, let's say, a plus b cosine, that kind of ellipse term, then this will force this v to be 1 over r squared. So basically, once you have this equation, then you can go back to solve that. If you plug the motion, the equation, the plug the orbits to this differential equation, then you will go back and solve this term to be 1 over r. Sorry, 1 over r. If you know your answer is ellipse. Yeah, so basically this is the strategy. And let me mention that there's another way to solve this one. So I will just quickly. So basically, you can also write. This is our equation, right? You can just write the two roots as this, and then you just directly integrate with these roots. And so basically this. Okay, and if you do this, then you can also show the answer is ellipse by this trigonometric substitution. But this will connect to general relativity. Because if you can show, if you go to the general relativity, you can prove that in the general relativity there will be some extra term here, so it will cause some the result the orbit is not exactly ellipse. Okay, so see you guys next videos.